Today I'd like to discuss the localization of rings, that is, introduce fractions for general rings. So suppose we start out with the commutative ring R. And we choose a subset of R which is multiplicatively closed. Namely, in the subset S, if we take any two elements, then their product also sits in S. And moreover, it contains the identity. So if S is multiplicatively closed, then we introduce a ring S minus 1R, which consists of numerators in R and denominators in the multiplicatively closed set. So this is already familiar in the case where R is an integral domain. That is, there are no non-trivial zero divisors. Then if we take S to be R without zero, then S minus 1 R will be the field of fractions of R. And there are hardly any subtleties. This is very much like going from Z to Q. But this is for an integral domain. However, in the general case, there are subtleties. Suppose that we have, for instance, S times A is equal to 0. Namely, we don't have an integral domain. We have an element A of R, which multiplied with an element S of S is equal to 0. If we have such a case, then we can see that naturally the fraction A over 1, which would be equal to the fraction SA over S, would be equal to 0 divided by S, which is equal to 0, and we would conclude correctly that A has to be set to 0 in the new ring. So what exactly do we have to set to 0? Well, if we have two fractions, R1 over S1 and R2 over S2, then this is not only 0 when the cross product is 0. So these are equivalent if the cross product is 0, or if we multiply by an element T of S, if there is an element T of S such that we multiply by T this cross product, and that is equal to 0, that is sufficient to say that these fractions are equivalent. So if there exists such an element, then these fractions are equivalent. And this does take care of the subtlety. Then we can just define addition normally, the product normally, and S minus 1R is a new ring in which we understand which fractions are equivalent. Another example is when we take the set of all regular elements, that is to say, all elements of the ring which are not zero divisors, then this ring will be called the total ring of fractions. So we already have the field of fractions. We have the total ring of fractions. We already gave the example where we went from Z to Q. So what are other examples? Another example, if we take S to be some set like 1, x, x squared, etc., which is multiplicatively closed, then if we localize the ring R with respect to S, which is this ring, it's canonically isomorphic to a ring over some other element S, where Sx is equal to 1. So we divide by the ideal generated by Sx minus 1. So I can check this. This is another example of localization. Another one is if we have a prime ideal in the ring R, then the set of all elements which is in the ring without the prime ideal is a multiplicatively closed set by the definition of prime ideal. Because a prime ideal has the property that if A, B is an element of P, then either A is an element of P or B is an element of P. So kind of like the reverse of this, if the product if the product in S would be in P, then it would have to be the case that one of the factors is in P, which is in contradiction with the fact that S is the complement of P. So therefore, S, which is the ring without the prime ideal, is the multiplicatively closed set. And we call R P, which is S minus 1 R, we call it the localization of the ring R at P. And it turns out that a lot of the properties of the ring R can be coded in its local properties. That is to say, in the properties of the localized rings with respect to its prime ideals. So this is a general tool to analyze rings, which generalizes the introduction of the fractions compared to the integers.